Welcome to Altair Engineering Training and Support. In this video, I am going to cover how to create 1D meshing for a roll cage structure, and then how to perform normal modal analysis in Radioss. So to perform normal modal analysis in HyperWorks, first we will create a 1D mesh data using HyperMesh. Then we will assign the proper material, then properties, and then we will create a load collectors. Then we assign some constraints on my model. Those are the suspension pickup points, that are the constraint points from where the reaction forces are going to come. So we are going to restrict it for degrees of freedom 1, 2, 3, that is transition along x, y and z axis for all the degrees of freedom, that is all the constraint pickup points. And then we will see the mode of different modes due to the frequency hertz. We will take the range as frequency from 1 hertz, that is the minimal frequency, to a range of 200 hertz, and then find out the different mode shapes. We will find for the first 10 mode shapes and then conclude that the maximum should not go beyond 100 hertz. So that should be below the 100 hertz range, and we find the different mode shapes for the roll cage structure. So the process which we are going to follow for normal modal analysis in HyperWorks is MPCLL, where first we create material as steel, then property in which we define the cross section using hyperbeam, and then define the 1D properties. Then we assign the proper properties and update the component collector. So all the 1D elements assigned proper material and properties. Then we create load collectors. Here we create one load collector for frequency range, which define the frequency range for my model, and the other one is constraint to apply constraint on my model. Then we define the type of analysis I am going to perform. For this normal modal analysis, I am going to use normal modal. Type of analysis will be normal modal for the Radioss structure. So we will start our analysis procedure. So to start the analysis procedure, first we have to import the model in IGS format, which contains the line data. So to import the model in IGS format, I will click on import button. First of all, I have to select the user profile as Radioss bulk data and say OK. Then I'll click on import button, select import geometry from the drop box, then click on the folder option. Before that, we should select a proper file type. As I have IGS file, so I will select IGS file type as IGS. If you have some other parts, CATIA file, step file, ProE file, or UG file, so you have to select that appropriately. Then click on folder option to browse the model. So I will open this roll cage line data.igs file and say open. Keep all the other parameters as default and then click on import. So once I click import, you will see my line data for the entire roll cage has been imported on my HyperMesh GUI. So I will close the import model. So now I step by step follow all the process, and then I will generate my normal modal analysis. So my first step is to assign material. So to assign material, I will click on material icon. For this particular roll cage structure, I am going to use material as steel. So I will name it as steel. Define an appropriate color. Then select the type of material. So I will select the type of material as isotropic. And then I will define the card image. We define card image to input additional parameters. Say in case of material, we have to define values of E, nu and rho to define the material properties. So different card image requires different input. So as per your requirement of the material selection, you have to select the different cards. there is a difference. I'll explain the difference between MAT1 and MAT4. As in MAT4 you can also include the thermal coefficient values. So if you want to perform a thermal analysis for certain structures, then you can select MAT4 as a card image and provide the thermal coefficient values so that it will take for the thermal analysis. If you don't, you can select MAT1, then click on create edit. Once you click on create edit, it will open the card edit panel to input different parameters related to the material properties. So for this material we require only E, nu and rho values to be as input. Then click return to exit the material card edit panel, and again click return to exit the material collector panel. So in this way we can see on my model browser my material has got created. Now my next step is to define the property. But before defining the property, I will define the cross section which I can include in the property collector. So to define the cross section I will use in Hyperbeam. In Hypermesh I will use Hyperbeam. So to enter the Hyperbeam panel, go to 1D page. In 1D page you will find Hyperbeam panel. This panel is used to define the cross sectional area. So click on Hyperbeam. In Hyperbeam panel, select the standard section as select the radio button for standard section, then select the standard section library as Hyperbeam and standard section type as thin wall tube. Then click on create. Once you click create, it will divert you towards the Hyperbeam window where you can see the actual cross section of the 1D elements. Then you have to just provide the outer and inner radius to create a hollow circular pipe. The rest of all the details it will calculate by its own. So like area, centroidal, moment of inertia, everything it calculates by own. So I will input the outer radius first. So the outer radius I am inputting for my roll cage structure is 12.7. It may vary from different structures to different structures, and inner radius as 12.0. So this is the cross sectional area for my roll cage structure. The pipes I am going to use for my roll cage structure is of this cross section. Once I define these two parameters, every other details the software calculates by its own. So now I will move to Hypermesh again to define property using this cross section. So I will click on this icon to move back to Hypermesh panel. So as you can see, once you create a beam section, it generates one more beam section model in your model browser. So a beam section has been created. Now I will use these beam section and define it in property collector. So I will click return to exit the Hyperbeam panel. Then to create property, I will click on property icon. For in property icon, first select the radio button for create. Enter the property name as roll cage 1D. Select an appropriate color for the property. Select the type of the element. As we are using 1D element, so I will select the type of the element as 1D. Then select the card image as P beam. Because we are using beam elements, so we'll select the property beam, that is P beam card image. Then we select the material, because we assign material in Hypermesh, we assign material in property, and then we assign property, proper property to the required components, and then the beam section which we have created. Then click on create edit to check whether or it has picked all the required values or not. So as you can see here, it has already picked due to the beam section. As you can see here, pick up beam section. So you can see here from the beam section it has picked all the required values. So I will click return to exit the card image panel of property. Again I will click return to exit the property collector icon. Then my next step is to update the component with proper property. To update the component, I will click on component icon. Select the radio button for update. Then click on comps and select the component which I want to update. So I am going to update this component with the appropriate property. In no property toggle, select the toggle, click on the toggle option and select it to property. Then click on property and then I select roll cage 1D and then click on update. So my component is updated with the required and proper property which contains the card image of P-beam. So my software will automatically takes the values for the 1D elements. Then it has assigned the steel material and card image as mat1. So my software, for the calculation point of view, it will take the values of material. Then I click return to exit the component collector. Now my next step is to define to create 1D elements. So in HyperMesh, to create 1D elements, you can go to 1D. In 1D, we have a line mesh option through which you can create 1D elements for the entire geometry at once. So I'll go to line mesh panel. In 1D page, go to line mesh panel. Make sure the line option is selected instead of node. So click on lines and say displayed. So it will select all the displayed lines. Then enter the element size. For the element size, I will enter here as 50. Then select the segment in a whole line, so it will create number of elements for this complete single lines. Select the elements configuration as bar 2 to define beam elements, and then select the property and click on roll cage which we have defined during the property collector icon. Then click on mesh. So once you click on mesh, you will find it has started generating the mesh for the entire 1D elements. Once it's create 1D elements, then click on return to exit the line mesh panel and finalize the mesh which it has generated. So in this way you can see my meshing has been done. So I will click return to exit the line mesh panel. So I can change the color also to view the elements more clearly, and then off the line geometries. So I will off this line geometry, so only my elements are visualized. Then I can move in HyperMesh. You have the options to see it as a 3D representation or 1D representation. So for 1D or 2D element in HyperMesh, the option is available to view the proper thickness or cross section assignment. That view, by just visualization you can find that whether the thickness is assigned or the cross section is assigned in case of 1D to each and every element or not. So you can see here my roll cage structure is completely defined with the appropriate thicknesses. So you can see here, if I mask any single element and say reverse, so you can find it here that it has been assigned with a proper cross sectional thickness. So I will click return. Now my next step is to define the load collectors and assign it on my model. So first I will define the load collector for constraint. So I will click on load collector icon to define the load collector for constraint. So in industries, mostly people use SPC to define constraint. SPC stands for single point constraint. So I will enter the name of the constraint as SPC, select an appropriate color, and then click on create to create the load collector. So now on my model browser you can see my load collector has been created. So I will click return to exit the load collector panel and assign it on my models. So now I will assign this to my model. To assign constraint on my model, go to analysis page. In analysis page, click on constraint panels. So now I'll click on constraint. So as I have shown you that I'm going to constrain this model for all the 16 pickup points, 8 at front, 8 at rear. So I will select the nodes for the pickup points. That is 8 at front. By left clicking on the nodes you can select that. So now you can see I have picked all the 16 suspension pickup points where I am going to constrain this model. For degree of freedom 1, 2, 3, DOF1 stands for translation along x-axis, DOF2 stands for translation along y-axis, DOF3 stands for translation along z-axis. So I am going to constrain this model for the all the three translational degrees of freedom. So I will click create to create this constraints. In hypermesh, constraints are represented using triangles, and these value 1, 2, 3 stands for this particular node is constrained for translation along 1, 2 and 3, that is translation along x, y and z axis. So I will click return to exit the constraint panel. Now my next step is to define one more load collector for the frequency range, where I can define the frequency range on which I am going to excite this roll cage structure. So I will again click on load collector to define a new load collector for the frequency range, where I can define the frequency range of my roll cage structure. So here I will enter it as load collector name as frequency, and on frequency, for the frequency load collector, I will toggle it down and select a card image. I will pick a card image as EIGRL. EIGRL card image, in EIGRL card image you can input the initial frequency and maximum frequency and also the number of modes. So you can input here. So once you enter the card image, select the appropriate color, a different color, and click on create edit. So here you can see, once you click on create edit, you will find V1, V2 and ND. V1 stands for initial frequency, V2 stands for maximum frequency, and ND stands for number of modes. So initial frequency for this particular roll cage structure I am taking as 1. Maximum frequency I am taking as 200. And for this range I am interested to find out 10 modes. So for the first 10 modes, what will be the eigenvalues for different modes, so that I will find out. Then I will click return to accept these values. Again I will click return to exit the load collector panel. Now my next step is to define the load step. So to define load step in hypermesh, I will go to analysis, load step. Then I will click on load step. In load step name, I will enter as normal modes. Select the type as normal modes. Check the box in front of SPC and select SPC. Then I'll check the box in front of method structure and select frequency. Then I click on create to create my load step, and then I'll click on return to exit the load step panel. So on my model browser, now you can see my load step, that is normal modes, has been defined. Now the next step is to save this file and run this model using Radioss as a solver. So I'll click on files, save as, create a new folder for naming as normal modes, save this file as normal modes. So my file has been saved. In hypermesh you will find on the GUI itself the proper location of the file. Then click on then to run this model using Radioss. In hypermesh GUI you can directly club with Radioss and OptiStruct solver. So in analysis page, click on Radioss to enter the Radioss panel. Then select the export option to all, memory option to analyze, memory option to default. Click the FEM file, save as, click on save as to save the FEM file. FEM file contains all the required data as meshing, material, properties, boundary conditions and load step, and then click on Radioss to start the analysis process. So now as you can see, my analysis has started. Once you see that analysis got completed message, that means your analysis has completed. Now click on results to view the results using hyperview. Once you click on results, your hyperview GUI will be opened. a new hyperview GUI has opened. So here here we will see the results for different modal analysis. So click on contour plot, then select the result type as Eigen modes and say apply. Then click on measures panel, click on measure panel to view the maximum Eigen mode for your model and the location of it, and click on play button to view the different modes or different animation due to the modes. As the value of animation is very less, so it is not visually very high, so we can maximize or scale the visualization of the different modes. So I will enter it as 10, so the animation has maximized. Or you can change the number of steps to 50 also, so it will be for a longer duration of time. So this is the animation due to the first modes, that is its maximum value is 18. For the second, its maximum value is 10 for second mode shape. Then for the third mode shape, the maximum value is coming as 11. For fourth mode shape, the maximum value is coming as 21. For fifth, it is coming as 12. For sixth, it is coming as 21. So all the mode shapes are below 100. That means the complete structure is safe. Then all the mode shape has to be less than 100. Then for the seventh, maximum is coming as 19th. For 8th, the maximum value is coming as 19. For 9th, it's 16. And for 10th, it is coming as 26. So in this way, you can see the different mode shapes using hypermesh. Using hyperview. So you can also increase the number of modes and also change the frequency range. So you have, for the modal analysis, which find the natural frequency should not, this Eigen frequency should not be more than the natural frequency of the structure. So as you can see, it's very below. So my structure is absolutely safe for the normal modal analysis, that is the frequency range. So in this way, we have ended with the video.